space is because after all, you are learning quantum computing. If you never heard about Hilbert space, people will laugh at you if you say you learn quantum computing or quantum mechanics, but you really don't need that. But however, you have been using that. It's not that you don't need that, it's you already know that. It just basically, I come back to teach you the associative law and distribution law in addition. But you never care about that. You already know that 1 + 2 = 2 + 1, right? That is what I'm trying to do. But this one will help you to understand what you're learning is really rigorous, and also you can appreciate what people say. Okay, so let's start with what is a Hilbert space? You don't have to memorize, but just a definition. What does it? It means it is a complete, right? We even don't know what is the meaning of complete. Linear, you know what is linear? Space. It is a space that is linear with inner product. That's interesting. So it is just a space with inner product. You need to define inner products inside this space, right? Like if you say the English alphabet, a Hilbert space, then you need to define what is the linear product between A and B. Now you can say A and B equal to C, B and B dot C equal to E, but eventually it will be self-consistent. So you have an inner product defined. This one, complete means they converge, right? But the exact meaning is very difficult to explain. So even I don't understand well, but just let you know. Yeah. Not that completeness. Yeah, not exactly. Yeah. So this I dump it to you to study from Wikipedia, which has a very complicated equation. But just know that 3 criteria: complete, linear space, and with inner product, right? That is for you to brag in front of people. If you don't understand, if you understand, that is good. You are better than me, right? But then, because you have the inner products, then we define this. Larger or equal. We define that the inner product is written as this bracket notation. Okay? So every vector inside I have an inner product. I define it. And you satisfy this criteria. This is the definition. Okay? So you don't ask why, but you find it makes sense now. Any vector inner product larger or equal to 0. Make sense? What is the meaning of inner product to itself? Just the length square, right? So of course the length has to be larger than 0, right? So this is the first rule. Second rule, if you have 2 vector FG, you do the inner product is equal to GF star. And that's why I say you know already. I already told you that is the different definition of the bracket when you do the inner product. But just now I go back to the very beginning. People will study what is Hilbert space first and then do the math, right? But now we already know the property. Just now you are the second grader, you already know 1 + 2 = 2 + 1. Now you go back, then people tell, oh, there's a very fancy term called commutative rule, which is very important, okay? And if I have a complex number times F, right? I scale the vector first. It is equal to this. Does this make sense to you? Have you learned this before? We have already, right? Because the broad version of F, if you scale it, is equal to its original. I mean, you scale F by C and find its broad version is equal to the broad version of F times C star, right? That we learned already, right? With this, you can easily prove that F of CG equals to what? If I want to take out the C. This one you also know already, even don't need to prove, but it can be proved. How about you tell me? I mean, equal to what times this? See? Just C, right? Because this is the cat version of G, right? We learned that before, but now this is a definition in the Hilbert space, when you have inner product. Okay, makes sense? Any questions?
Do they have Hilbert space first or broadcast?
Do they have what say?
Hilbert space, the idea has Hilbert space first or the broadcast first?
I don't know. I think Hilbert space probably. I mean, formally, you should start with Hilbert space. Yes, I think so. Yeah. Yeah. So now you have this F1 plus F2 with G. What is this? You know already, right? Distribution law. How will you write it? Distribution law. F1 inner product with G plus F2 inner product with G. Thank you, right? So you find that now at the beginning, if I tell you what is Hilbert space in the first class, you find they are meaningless and just a lot of definition. But now you see that, wow, what we are doing, what we have been learning is a Hilbert space, nothing special, right? You have some very important criteria like compete and convergence, but after that, it is easy, right? So then this is a Hilbert space. So you see that Hilbert space is simple, right? I just want to remind you, what I'm showing here is called physical convention, just a convention. That what the physicists do, okay? There is a mathematical convention that the math people like to write, is that they want to write it as, instead of bracket, they write it as comma. Okay, just for your information, because I read it from the book, I think it's good to say it. For example, instead we would say CF comma G equal to C star FG. Okay. Yeah, it just the symbol is different, right? So it doesn't matter, right? We will play with the physics one. Okay. So then finally, what I want to say is any finite dimensional vector space with a linear product is a Hilbert space. Right, so you see that because it's finite dimensional, then it is complete. Right, complete is a very special definition. Again, I forgot what it is. That's why I asked you to look at wiki. Right, but basically, you need just as long as it's finite dimensional within the product, then it is Hilbert space. Now, you think about when we talk about the yes and no space, right? The girl space. I don't know if we define the inner product. We kind of define the inner product. I don't know, right? If we define the inner product, that is a Hilbert space. And definitely for electrons, spin up and spin down is a Hilbert space because it's a finite dimensional vector space. Okay. Now, then why we do need to learn that yet? Basically, is that how we build a bigger space from a more fundamental space. For example, English, you can say it is a space. Its basis vector are A, B, C, D, all the way to Z. You can say it's a 26 dimensional space. Is it 26? Not 24, right? Anyway, and then you have also Japanese. It has all the basic character. It has its own space, right? Now, all the Japanese character space can only write a book in Japanese. And each book is a vector in that space. And I say that it's not a good analogy, but anyway, it formed the space. The English letter also formed its own space, right? Now, what if I form a larger space by using the English basis and the Japanese space? Just match the character together. Then I can write anything in terms of Japanese and English. And not just that, I can put an English word after a Japanese word. In principle, I can also put A after a Japanese character, right? I can mix that. So the space is really large. And how do you mix them? You just do permutation, do whatever way you can combine them. And that is a tensor product. There's a very hand-waving, maybe wrong analogy, but basically this is what we're saying here. If I have a space H1 and H2, they're both Hilbert space. Right? I can define a larger space H3, which is the tensor product of H1 and H2. I want to define that, just like I have Japanese and English character, Japanese space, English space. I combine them, becomes English-Japanese space. Now, then for a vector inside the H, for example, a verb in English, F, and a verb in Japanese like G inside H, right? After this space is formed, I can have even complicated vector in this larger space. What is the relationship between this vector in this larger space to the vector in those smaller space? You will always be able to write this vector in H3, the tensor product of H1 and H2, as a linear combination of the tensor product of the individual vector. Basically, this so-called tensor product is nothing but just you put them together, put in one next to each other, right? So here I gave an example. For example, H may be equals to this. Then it means alpha 0, right? This I is 1 over square root 2. F0 is 0. G0 is 0. And then alpha 1, this summation, right, is I over square root 2. F1 can be 1. G can be plus, can be a more complicated. But these are all inside the smaller space. Now, I want you to be very careful when you look at this. When I write 0 tensor product 0, they are both 0, but they are not equal to each other. This is the 0 in the first space. So it is the 0 for the first electron. This is 0 in the second space, the 0 of the second electron. Okay, so you cannot swap them. You can say, I want to call the second electron the first, then you swap them. But then for the rest, you need to do the same thing. You need to follow the order clearly when you form a larger space. I know it's still very vague what is a tensor product. I give you a high-level description, but later we will do some numerical substitution, then you will understand better. You basically don't need to know these rules. I don't need you to do this in the exam, but I want you to feel very comfortable with this. For example, I say C times F tensor product G is equals to F tensor product CG or CF tensor product G. Can anyone explain to me in English what it means? C is a complex number. C is not a vector. It's a number. What am I saying here? This one, what is it in English? Let me tell you. I do a tensor product of F in the first space with G in the second space. Okay? It's just I do a word in English and combine it with a word in Japanese. And then I scale the final, this becomes the vector in the larger space. I scale this one by C, a number, multiply it by 2. It's the same as I scale the vector in the second space by 2, multiply it first, and then do a tensor product with the F in the tensor product space. Okay? How about let's use Greek and English, right? For example, what it is saying is this. 2 times alpha 2 times A tensor product alpha equals to A tensor product 2 alpha or 2 A, the whole thing, tensor product alpha. This is a fake example, but this is the English space, this is the Greek space. Okay? Do not take it too seriously, but this is what I'm trying to say, yeah. Is the tensor product, say again? You're just combining two things together, that's it. The tensor product, yeah, you just permutate them. For the what in the Hilbert space? Array? Vector, yes. Yeah. You can, maybe I should say, you just put them adjacent to each other. Yeah, then it becomes a new vector in the new space. You can say that, yeah. Yeah, vector, right? You mean vector. A vector in the, yeah. But not linear combination. Make it clear. You don't form a 2D plane. X, this one is not equal to X plus this one. This is just, I write it down, that's it, X, Y. No meaning, that's it, okay? But X plus Y, you're really talking about a vector, which is a linear combination of X hat and Y hat. Okay, it is confused, yeah. The point is you don't need to exist. F is any vector in H1, G is any H vector in H2, and you just take them, combine them, then you form the larger space. They don't have to be equivalent. They don't have to. Here is just an example. This G can repeat. You see, here I did not. For example, this can be 0, right? 0 tensor product 0 plus 10, 0 times plus. Let's say I only have 0, one vector, and then I can have two vectors in another space. Yeah. Let's continue. Yes, swallow it first, then later you know better. But yes, you need to keep thinking. For example, this is a good question here, right? It is not the same, right? It's not the same. Tensor product is not you add two vectors from different spaces together. Because they are in two different spaces, you cannot add them. They don't talk to each other. They are in different universe. Okay? But you can combine, say now I have a bigger universe containing these two smaller universes. Okay, so they also obey the linear, the distribution law, right? One product, what is the meaning of this one? Anyone want to say this in English? What's the meaning on the one on left? Like what I've been telling you what to do, can you? Anyone volunteer? What is this saying? Very good. You add two vectors in the first space, then do the tensor product with a vector in the second space. It's the same as you first do the tensor product of the first space and the second space plus the tensor product of the second vector in the first space with that of the second space. Okay, now this plus is meaningful now because it's talking about the addition of two vectors in the same space. Both of them belong to H3. This plus also meaningful because it's talking about the addition of two vectors in the same space. Both belong to H1. Now, I know it's confusing, but I want you to take it and swallow it as a definition. Okay? You just agree on this first. Then we look at an example. And similarly with this is not difficult to understand. It's just telling us that it's the same whether it's from left or to the right. Yeah, anyone want to say what it is? What is the meaning of this again? Just like what I told you earlier. Someone want to say it? What same thing? Say it. Right. Very good. Yeah. So I actually have some typo here. The tensor product of F in the first space with a sum of two vectors in the second space, you sum them first and then do tensor product. It's the same as you do the tensor product individually and then sum them. Okay? Now, the last one, this is actually fourth, right? The last one is actually difficult to swallow, but let me write it down. It's just a challenge for you. This line is more a psychological exercise. I want you to feel comfortable, not afraid of this anymore. Although it's not useful in our class because we don't use it for derivation, but you use the law as now what you do for addition and subtraction. Okay? Look at this one. I want you to be able to tell me what it means. Right, so this is very complicated. So here I'm saying that I have four vectors, H, L, F, J, G, I, K, L. H and F belong to the first space, H1. G, I, K, L belong to the second space, H2. What is this one telling us? You should be able to read it. What is this symbol talking about? First of all, what is this? Inner product. So what it say? It's saying that this is the inner product of one vector and another vector. What is this vector? It's a tensor product of the vector in the first space and the second space, but we have some linear combination, right? It's not a simple tensor product. Yes, a something tensor product plus something tensor product, but still it is a tensor product. How about the next one? What does it say? It's the same, right? It's also a vector in the H3 space, and it is a tensor product of the vector in the first space and the second space. So I form a vector from the H1 and H2, and in the high space, higher dimensional space, H3, I do a tensor product with another vector. That's it. That's what you're saying, right? And this one, so this one is just the condition, equals to this. Can you tell me what does this say? The tensor products of two vectors in the H3 dimension in which this vector are linear combination of the tensor product of the lower dimension, equals to what? What is the meaning of this? FJHL. Now, look at it. You are almost correct. FJ is in which space? How about HL? HL, which space? Same H. They are from the same space. So it is saying that this is the summation, right? You do the inner product in the higher dimension, okay? It's the same as you do the inner product at the lower dimension individually first, and then you do multiplication. The result is the same. Now, this one, then let me say again. So this means the inner product of each of the vector in the H1 space times, which is a number, times the inner product of the vector in the H2, okay? You multiply them, sum them, is the same as you do the inner product after you construct the higher dimensional vector. Now, this one, you don't need to memorize, even no need to write in cheat sheet. The point, yeah.
Is it G?
Thank you. GJ. Should be GJ, yeah. So this one, as I say, is more like a psychological exercise. You need to be very brave when you see this. You say, I understand. All I need to do is just to break it down. I recognize this is inner product, so this must be vector, and indeed it is vector. What vector is this? Well, it's a tensor product from the lower dimension. I don't know what it is. Someone give me a bunch of vector. I do tensor product, I add them together, and that is my vector in the higher dimension. The inner product of these two vectors is the same as I do the components inner product in their lower dimension first, and then multiply them together. Okay? Yeah. Which two components? These two? Okay. What is this? A number, vector, or matrix? Number, right? Yeah, very good. Right, so because it's number, so it must be a regular multiplication, right? 2 times 3, 3 times 4. Okay? Good. Don't worry too much. I want to show you the worst thing in this class, which is not required in the exam. But you will see that tensor product looks very fancy, looks very difficult, but turn out to be very simple because it obeys the distribution rule. It obeys even this rule. So I can do it in high dimension or low dimension. Very often I just do operation in low dimension and then combine it together. The result is the same as I operating in the high dimension. So tensor product is very simple. Just combine the lower dimension thing together, right? So I will skip